Okay, it's my pleasure to introduce Dr. Daniel Barrero, who was born in Bogota, Colombia, and came to the United States to study physics, earning his Bachelor's of Science from the University of Texas, hook 'em horns. I got my master's there, and his PhD from Georgia Tech. In 2016, Daniel joined the faculty of Willamette Department of Physics, where he researches fluid systems with complex spatiotemporal dynamics and emergent phenomena such as spontaneous synchronization in mechanical systems. You will be pleased to know he's not talking about that today. But today he is recounting an important historical moment in physics and the controversy that has surrounded it. And in kind of a serendipitous thing, I want to point out that Bob Muir mentioned this event in his talk on Tuesday because a woman astronomer was involved in the work. Please welcome Dr. Barrero.
All right. Can people hear me okay? Can people hear me okay? Awesome. Cool. So as was just mentioned, this is actually not my research specialty, but I do encourage you to invite me to talk about the spatiotemporal dynamics stuff, because it's actually really cool, and there's a lot of very cool videos, just a lot of big words. I'll send a teaser out, and you all can decide whether you want to hear about spatiotemporal dynamics, complex spatiotemporal dynamics. Yeah, I can't even say it. Okay, so today's talk is going to span the 2 hours. So the first half of the talk is going to be sort of a crash course in relativity. So get your math brains ready to go. And then the second half, we're going to talk about a famous experiment called the Eddington experiment, and the attempt that my students and I and our collaborators made last year to try to recreate it, and the adventures that ensued. Okay, so let's start our story. And does this mouse work? Yeah, let me just see. Yeah, no, I'm just getting the pointer, set up. Oops, where are you? Right. This guy. All right, cool. So just in case I need it. Okay, so our story kind of begins way back in the late 1500s, early 1600s, with the work of Galileo, right? And Galileo is a giant amongst sort of early scientists who, amongst many other things, tried to show that Copernicus' earlier theory of a heliocentric solar system, right? This is where the sun is at the center of the solar system, was correct, as opposed to the more prevailing theory that had stuck around since the time of Aristotle and even before, that the Earth was at the center of the universe, right? Well, he did not invent the telescope. He was a very early adopter. It's actually disputed who invented the telescope, because there's like 3 guys that filed patents within like a week of each other. But anyway, Galileo has this sort of brilliant idea that rather than using the telescope to do this and spy on your enemies from the ramparts in your castles or whatever, you could do this. So, really brilliant guy, groundbreaker. And so he points the telescopes to the heavens and make a bunch of interesting astronomical discoveries that hadn't been made before. He also is sort of important because he publishes his findings in Italian as opposed to Latin. So this makes him a lot more accessible to the general public, and this is also kind of a big deal, right? Importantly, he believes that scientific theories need to be tested against the experiments, right? This conflicts with sort of the Greeks, ancient Greeks' view that, you could just think your way to truth. Galileo sort of thinks that you need to check against reality. Again, giant, groundbreaking idea, like pointing your telescope into the sky. Okay. So anyway, before I get into sort of the meat of the talk, I did want to bring this up because I like these slides. I use them in my astronomy class. And so here's what Galileo saw when he pointed his telescope at the sky. One of the first things he noticed was if he looked at Jupiter, he noticed that so here's Jupiter, the little circle, and then he noticed that there was these other little bright dots around it, and over time, over the course of days, they kind of moved around relative to Jupiter, and he interpreted those as moons, right? And so this was a big deal because one of the sort of critiques of the heliocentric model was, well, if the Earth is just another planet, why are we the only one that has a moon? So Galileo kind of shows that other planets can also have moons. He's able to determine that there's mountains on Mars, on the moon, and he does that by sort of looking at the light leaking sort of through valleys between mountains when we have sort of a half lit up moon, and he interprets that as mountains. He's also able to observe the phases of Venus, which had been predicted by Copernicus and other scientists, but hadn't been observed directly because you just didn't have the resolution with naked eye observations. The cool thing about this slide, though, is actually to show you what we can see now with our modern technology. So, wait, what happened? No. Oh, I know what happened. Hold on, I'll fix it. I got you. They're just hidden. Where does it say on hide slide? Okay, that's the problem. So, redo. Okay, so this is what Galileo saw and wrote down, right? It didn't have cameras, didn't have film. And so this is what we see today. So here's Jupiter, right? And you can actually see the little moons and their little shadows on Jupiter. So that's kind of cool. Obviously, ever since the Apollo era, we have close-up pictures of the mountains on the moon. So that's pretty cool. We've even sent probes out to Jupiter's moons. And here, for example, is Jupiter's moon Io. And here we can see a little volcano going off on it, too, which is kind of cool. But it's a volcano made of ice, which is kind of interesting. And here's sort of a series of images of the phases of Venus. So it has phases much like our moon does. Okay. He also was one of the first to note sunspots and also the rings of Saturn. So with his first telescope, he has this kind of sketch that's like Saturn with some stuff on the sides of it. Then as he makes sort of better and better telescopes, he is able to get better and better images. And of course, today we have really impressive photographs of both of these things. So here's the disk of the sun with a bunch of sunspots on it. Here's some close-ups. Notice that the sunspots aren't actually black. They're just a lot dimmer than the surrounding material. So when we put filters to sort of dim the sun down enough for us to be able to see, they appear black, but they're actually really bright too. And then here's, of course, Saturn in different orientations, and we can see the rings. Okay, so anyway, that was just kind of cool and not super related to the rest of the talk. But let's talk a little bit more about what Galileo did. So he disputed this classical Aristotelian physics, which basically what Aristotle had said, about 1,500 years earlier, was, well, stuff is made out of the 4 basic elements, right? There's really 5 if you include ether, which makes stars, and stars sort of behave differently. But everything else is made out of like earth, wind, fire, and water, right? And where things go sort of depends on what their composition is. So earth is heavier, so things that are earthier kind of go lower. Things that are made up of fire, it's sort of lighter, go up. And then everything kind of settles depending on effectively sort of its density, and then stops, right? Galileo kind of challenges this idea and starts doing experiments to try to understand how things work. And we'll go over some of those. So one important area, and we'll be referring to Galilean relativity in a little bit, is he starts thinking about how things look like to different observers, right? So if Galileo is doing an experiment, for example, seeing how objects drop, and he's on a ship, what does he see as opposed to somebody who's on the shore watching him do this experiment, and how do those 2 points of view differ, right? So this is the idea of relative motion. He also studies inertia, right? And so this is one really is the big challenge to Aristotelian physics, and we'll talk a lot more about that one. And this is sort of the idea that things kind of have inertia and tend to keep moving the way they're doing unless we do something to them. He studies the physics of falling bodies, right? So sort of perhaps apocryphally, but he shows that things take the same amount of time to fall if you throw them off the Tower of Pisa, as long as you sort of take some precautions to ward off the effects of air resistance. And finally, he, of course, is being paid by all these Italian dukes that are fighting each other, so they're very interested in shooting things. And so he studies the physics of projectiles and how the trajectories of projectiles. Okay. All right. Okay, so now fast forward about 50 years or so, and we come to Newton. So while Galileo was a great experimentalist and did some math, we really just didn't have the math to really do physics. And then Newton comes around. Basically, there's a plague, and the college shuts down. He goes home for 18 months, and in those 18 months, just kind of sitting around, invents like basically all of classical mechanics and calculus during the COVID break, basically. So that's pretty kind of impressive output for a single person, and of course that makes him one of the greatest physicists and scientists of all time. He's able to basically show that these two problems, the problem of sort of projectiles and falling bodies, and the problem of the orbits of the planets end up being basically the same problem, except he provides a unifying framework. And he does this in formulating what are now known as Newton's laws of motion, right? There's three of them, we'll talk about them, and also his law of universal gravitation. And then he does a bunch of other interesting things, like he studies optics a lot, invents the first telescope that's based on mirrors. So if you remember last semester, I talked about the James Webb Space Telescope and how it uses mirrors instead of lenses to create images. Newton's the first to come up with that type of design, right? And as I mentioned, he also invented calculus, which you kind of need to be able to do anything with his three laws of motion. Okay, so let's talk about Newton's laws. So the first law is basically just a reformulation of Galileo's result, which says that if we have an object and its sort of natural tendency is if it's at rest, it's going to stay at rest, right? And then if it's moving, it's going to continue moving in a straight line at a constant speed unless we do something to change that. So unless an external force acts on this, right? And so sometimes we'll call this the law of inertia. Now, Galileo, the way Galileo figured this out is actually kind of interesting and shows you sort of how clever he was. So what Galileo did was he had these ramps built, and they had these little bells so you could hear them ding, ding, ding when a little ball rolled down them. And then he was timing stuff with his pulse. But anyway, what he figured out was, suppose I take a ramp and roll a ball down it, right? And then I put a ramp that's exactly the same on the opposite side. Well, it'll roll up and stop, right? And if I make a less steep ramp, it'll roll up and stop. But the time that it does to get back up here gets longer, right? Which then means that on average, the ball has to go slower here, right? Or not slower, sorry. So the time gets longer and longer, right? And then as you lower and lower the angle, that time gets longer and longer, and the ball just takes longer to stop, right? And so Galileo, by extension, says, well, if we take the ramp all the way to flat, then the object will never stop, right? Because the time will go to infinity. And so that's kind of a clever leap that he takes there. Because, of course, in everyday experience, we have friction in that, remember the first law here says, unless acted on by a force. So once we introduce friction, things are kind of a problem. Okay, so anyway, Newton's first law sort of codifies this idea that unless there's enough of force acting, and really it's a net force, acting on an object, it's going to either stay at rest if it's at rest, or move in a straight line at constant speed if it's moving at all. Right? Okay, so that's Newton's first law. Newton's second law sort of codifies how this all works once we do add a force. And he basically says, well, if I push on something or pull on something, so I exert a force, I'm going to cause its motion to change. And that's going to be captured by acceleration, right? So remember, if I don't exert a force, it's going to move at constant speed. So if I exert a force, I can change its speed, which we, in everyday speak, call accelerate, right? Or decelerate. In physics, we'll just call it accelerate, and the acceleration can be positive or negative. But the point is we can change its speed, right? And then the other thing is that the first law said is that we'll move in a straight line, right? So if I exert a force, I can cause things to not move in a straight line. And that's also captured in acceleration. So acceleration in physics is a change in how fast you're going or a change in which direction you're going, right? And what Newton tells us is, well, for a given force, so if I push with a certain amount of push, how my acceleration changes, or how my velocity changes, how much acceleration I get, is proportional to each other. So more force, more acceleration. That kind of makes sense. Push harder, things speed up more, right? But then there's an additional sort of proportionality constant there, which is the mass of the object. So if I push a given amount on a little tiny, light object, it's going to change its motion a lot. If I, on the other hand, I try to push a building, I'm not going to do very much, right? So that's what Newton's second law, which sort of famously is written down as F equals ma in introductory physics textbooks. That's what it says. It basically just says, for a given push, the harder I push, the more the motion changes, but how much it changes depends on how massive my object is. More massive objects are harder to get to change their motion than lighter objects, right? And as an example, you can imagine pushing a cart, right? For a given push, if I have an empty cart, I can really get it going. For a loaded up cart, went to Costco, really loaded up on some deals. I really need to kind of get behind it to get it to accelerate a good amount, right? Okay, so that's Newton's second law. Newton's third law, so here's an example. So obviously, one simple example is things falling, right? So if I start with an object and I let it go, there's a force, that's the gravitational force, and that causes it to go from rest, right? And then speed up as it falls down, right? So here we see acceleration due to a force, right? And here, what's changing is how fast the thing is going. We can also see this video here. And in this video, we're going to roll, or this person is going to roll this bowling ball, right? It's good and heavy. It doesn't really want to change the way it's moving. It's going to try to move in a straight line at constant speed. And then the other person has, I guess it's a croquet mallet. I'm not super sure. And let's see, can I do this with the pointer? Maybe not. How do I get rid of the pointer? Play. Not a highlighter. I want just the pointer. Let's do this. This will definitely do it. Oh, there we go. Okay. So here we go. So here's the video. Ball starts moving at a constant rate, and then they're going to hit it perpendicular to the direction of motion. And you can get it to curve until, obviously, physics professor, not super in shape, kind of runs out of breath. And, and then as soon as he stops forcing it, right, it goes in a straight line at a constant speed. Right, so this is a nice example of inertia and of Newton's second law. Not pen, pointer, in case we need it. Okay. So that's Newton's second law. Newton's third law won't be super relevant for this talk, but for completeness, I'll talk about it. It basically is the famous for every action there is an equal and opposite reaction, right? And it basically just tells us that forces come in pairs. If object A exerts a force on object B, then B exerts a force back on object A that happens to have the same magnitude. It's just as big as, but in the opposite direction, right? And so we have some examples from everyday life and then from shuttle, which is sort of my favorite space vehicle. But if you push on the ground, right, when I drag my feet to step, I push back on the ground and then the ground pushes me forward, right? But because the ground, right, the Earth is supermassive, the Earth doesn't really go anywhere, whereas me, lightish compared to the Earth, I do get propelled forward, right, and accelerate and change my motion from being at rest to being in motion, right? And in the case of the shuttle, right, we have the shuttle uses, generates a force on the propellant down, and then the propellant pushes the shuttle up, right, and causes it to go up. By the way, this is sort of super tangential, but if anybody really has time to listen to podcasts, there's this amazing podcast right now called 16 Sunsets about the space shuttle program. It's super duper cool. So highly recommend. 16 Sunsets. Yep. All right. Okay, so question for y'all, quiz. So suppose we have the Earth, and we know that it goes around the sun, and it's an elliptical orbit, but it's approximately circular. Is there a force acting on the Earth, and how can we tell? So think about it for a sec, and then we'll vote. All right, how many people think the answer is A, yes? Okay, wow, good students. Yeah, so the correct answer is yes, right? And how do we know? Because it's not going in a straight line at constant speed, right? And so that means there has to be a force acting on it. In this case, of course, the force is going to be gravity. The sun's gravitational force is pulling the Earth towards the sun everywhere on its orbit, causing it to curve, right? Remember, if that force was perpendicular to the direction of the motion, like the mallet, the trajectory curves. Right? Formally speaking, it also speeds it up and slows it down on the orbit because the orbit isn't perfectly circular, but that's details. All right. Now, in order to actually do any math, though, we need to be able to compute what the gravitational force is, for example, right? And Newton also tells us how to do this, right? And so this is his universal law of gravitation, and it tells us how to compute the gravitational forces between objects. In particular, it tells us if we have an object with mass 1, right, and then an object with mass 2 that are separated by a distance r, then the magnitude of the gravitational force that, say, 1 exerts on 2, or that 2 exerts on 1, right? Remember, Newton's third law tells us that those should have the same magnitude anyway, just point in opposite directions, is given by this equation here, which just tells us that the gravitational force increases as I increase my masses, so bigger masses, more gravity. That kind of makes sense, right? Well, maybe. I guess at Newton's time it didn't necessarily make sense. But more gravity, more mass, more gravity, right? And that's why there's a significant gravitational force between me and the Earth, but I'm not getting pulled over here towards y'all, right? Because y'all aren't quite as heavy as the Earth. Right? So this just tells me as I increase my masses, I have a stronger gravitational force. And that's why the sun, which is ridiculously massive, can actually cause the Earth's orbit to curve, right? If it was a small force, I would see very little change in the Earth's orbit. But because we have this massive, really massive sun, I get a really strong force that is actually able to curve the trajectory of the Earth, right? And then the other part is under here. And that tells me that it's inversely proportional to the square of the separation. So as things get further away, the force gets weaker. Okay? And then there's a proportionality constant g, which we don't need to worry about. That just makes it so the units all work out and so forth. It tells us something about how strong the force of gravity is compared to other forces, but it doesn't super matter. Okay? Okay, so one thing that we can do is we can start with Newton's second law. Remember Newton's second law, right, told us F is equal to ma. So if I take this thing and flip it around, if I want to compute A, I can just figure out what the force is and divide by the mass, right? And that's going to tell me how much acceleration I get. So I can do that for objects near the surface of the Earth. And if I do that, I'm going to get that the acceleration A is just the force of gravity between the object and the Earth divided by the mass of the object. I just plug in my Newton's law of universal gravitation, do some algebra. If you're rusty in your algebra, don't worry about it. But the point is you get g times, now this m1 is going to be the mass of the Earth, divided by, well, for objects near the surface of the Earth, the separation between us and the center of the Earth is basically the radius of the Earth, right? Plus or minus like a meter or something, so it doesn't really make a huge deal. Now, the interesting thing is this quantity only depends on the mass of the Earth and on the radius of the Earth, right? So what this tells us is that all objects are going to accelerate the same when they're falling near the surface of the Earth, right? And so this was Galileo's result from the Tower of Pisa, was that all objects, if we make sure that we don't have air resistance or mitigate it, should fall at the same rate, right? So Newton is able to explain that, right? And so I wanted to show you this video because it's super duper cool. And so it is from,
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space. And it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of...
So that's kind of interesting that air is that heavy, right? Like we don't really think about air as being heavy, but this big tank is 30 tons of air, and they really pump it down, right? And you end up with 2 grams. That's like not a lot of air left in there.
It's got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
Those look like they're from the 60s.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
All right, this guy here is like my favorite guy in the entire video. He's probably got like a PhD in aerospace engineering and has been working at NASA for like decades and definitely trusts that Newton's laws are correct. But just watch him, He's just like, can't believe it.
Exactly the same. Wow.
Look at how they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
So anyway, that video is super cool. Not super, only marginally related to the rest of the talk, but but basically it shows us that Newton's laws work pretty well, right? And that what Newton came up with by sitting around during the plague and actually works. Okay, so just to recap, Newton's mechanics is sort of summarized in his 3 laws of motion, and then plus his law of universal gravitation, as far as we're thinking about space things, that's going to be the most important force. And then other people try to figure out how other forces work. So for example, Hooke tried to figure out how spring forces work. That's kind of another fun story. So Newton and Hooke were butting heads with each other at the Royal Society. And when Hooke died, Newton had all the portraits of Hooke burned because he hated him so much. So anyway, Robert Hooke, also one of the early adopters of the microscope and discovered the biological cell, right? Called them cells because they looked like the cells in like a nunnery or a monastery. Right? Little. Okay, anyway, neither here nor there. Okay, so let's now think about things in different frames of reference. So suppose, and I was going to bring a ball, but I forgot. Let's see, maybe I have a marker in here. Okay, so we have a marker, right? And I'm running at constant speed, and I'm just going to let it go, right? And we want to try to think about what it looks like from your all's perspective, right? So camera fixed on the ground, and what it would look like if we had a camera on a dolly running at the same, or moving along at the same speed that I do, right? And so I guess I'll hold it on this hand. So I'm going to go. All right. So, what do you think? Maybe take a minute and chat with your neighbors and see what you think the two videos would look like.
Is the dolly is the camera focused on the pen or you?
Or
Does it matter?
but it doesn't super matter, but say the pen. Oh, another question, sorry? If I would run again. Okay, let's do this again. And, all right, here we go. All right. I'll do it the other way since I need to go back there anyway. We said physics professor's out of shape. You can call the exercise and health science people over if you want. A lot of running. Yeah, question? Oh, sorry, there was two people with raised hands. You in the front?
It looks like maybe the pen is going this way from one perspective.
Okay, so you think it's yeah. So it wasn't a question. I guess it was just an answer, really. So let's start with the first one. So if the camera relative to you, what happens? Does it go straight down? No, it looks kind of like what you're saying, right? It goes down, and really it's speeding up as it goes down, right? Because it starts from rest and water bottle starts from rest and speeds up as it falls, right? So it goes faster and faster. So really, it's going to look something kind of like this, right? If we're looking at snapshots at constant intervals in time, initially it's moving slowly, so it doesn't change a lot between frames, and then eventually it hits the ground, right? Maybe bounces a little bit. Okay. All right, so that's from your all's point of view. What would happen if we were sitting on that dolly, like filming it? It goes straight down, right? It just looks good. Boop. And that's because we don't have a force going this way if we ignore air resistance, right? And so the motion can't change in this direction. It can only change in the direction that the force is, right? So it'll just speed down, right? So we can see that different points of view, different frames of reference are going to give us sort of different trajectories. And one of the things we might want to figure out, and this is sort of the thing that Galileo was thinking about when he was talking or investigating relative motion, is what do different observers see. So let's go ahead and see how that works. So suppose that we're in a train car, and it's on some tracks that are nice and smooth, not like the ones over here by 12th Street. And we have an air hockey table in it. And the train is moving along at constant speed. And the tracks are super smooth, so you can't feel it rattling or anything. And then your air kids are bored because this train car has no windows and you can't even see outside, and they're playing air hockey, right? Does that air hockey game look any different than if you were sitting at Pietro's Pizza watching them play? Have some yeses, nos. Okay, so if you said yes, how would it look different? Well, but this is moving at constant speed, right? You had a, yeah.
If you're standing outside the train, the air hockey's going this way. If it isn't moving, then it's just going this way.
Yeah, so if here we're talking from inside the train, right? So outside the train, yeah, the air hockey table is moving along with the train, right? And from inside the train, it looks the same, right? We can't really tell the difference between sitting at Pietro's playing air hockey or sitting in this train that's moving along at constant speed, right? Okay. So, and this little part, I'll skip it. But basically what this tells us is that really there isn't anything that I can do to figure out whether I'm moving at a constant speed or if I'm at rest, right? Because all these mechanical systems work exactly the same way if I'm in a reference frame that's moving at constant speed and direction as if I'm moving, as if I'm at rest, right? Okay, now, suppose that, And by the way, I guess this tells us that, for example, if I start the puck at rest, right, and I'm inside the train, it stays at rest. It doesn't just start moving randomly, right? And if I do that and watch it from the outside, it will move at constant speed with the train, right? And so basically what that tells us is that in this reference frame, Newton's first law, which was that law of inertia, holds, right? And so we'll say that these reference frames are inertial reference frames because the law of inertia holds. That's basically all inertial reference frame means, right? Let's see how we're doing on time. Okay. Okay, so now let's do something different, right? So your grandkid Susie just got scored on and wants to take her first shot after a goal, but then the train moves into the station and starts slowing down. So puck is at rest. Susie's getting ready to whack it. What does the puck do now? All right, so think about it for a second, then we'll vote. And I guess feel free to discuss with your neighbors if you want. Convince them why they're wrong. All right, so how many people think the answer is A? How many people think it's B? How many people think it's C? Yeah. So the correct answer is A, right? It's kind of like when if you slam the brakes on a car, right? And that's a lot of inertia at play, right? Your body or the puck wants to keep going forward in a straight line at constant speed, but the car is slowing down and under them, right? Or the train car is slowing down and under them. So, okay. So this is different, right? Because for example, if you were Susie and you had your puck, it was sitting still, you didn't do anything to it, all of a sudden it just started moving, right? That would be weird, right? Things in our usual experience don't just start moving, right? And so this tells us that there's something slightly different about this situation than the previous situation. Because in the previous situation, stuff that was at rest stays at rest, and stuff that was in motion stays in motion, and inertia holds, right? Here, inertia doesn't hold. Things just start moving, right? And so we say that this is not an inertial frame, right? And so what we'll call reference frames in which Newton's first law doesn't hold a non-inertial or accelerated reference frame, right? And this is because the actual train car is accelerating, its speed is changing. All right. Okay, so the conclusion here is that physics is different between inertial frames and non-inertial frames, right? Because in non-inertial frames, things can just start moving. And that's just because the reference frame is moving, is accelerating around them. Okay, so now a little bit of math. So it's all right, you'll survive this. Okay. So let's go ahead and put the pen up here. Oop, nope, not the pen. Always the pen, not the pen, but the pointer. Okay, so suppose that we have two observers, right? And so one of them is standing, say, by the side of the railroad tracks. They're not moving, and there's some object that they determine to be at the position x is equal to 2. And we'll call any measurement that they make the unprimed frame. Whereas this moving observer, say they're moving in the train, right? We'll call that observer S prime with this little prime symbol here. And let's say they're moving along at 1 meter per second this way, and then these are just positions in meters. So for observer S, the ball is at x is equal to 2. And then at the initial time, we'll assume that these two observers are at the same location, so x and x prime equals 0. Right? But, and so for the second observer, the ball is also at t equals 0, is at x prime is equal to 2. Right? Any questions about that? Yeah, question? Oh, no, it was just a comment. Right? So this is pretty simple, but it'll get confusing in a sec. So, okay, so now let's think about what happens sometime later. So at t equals 0, s measured x equals 2 and s prime measured x equals 2, right? But sometime later, we have that s prime is going to move, right? They're in the moving reference frame. And so they're going to move, well, if my speed is 1 meter per second and I move for 3 seconds, I'm going to move 1 meter in the first second, a second meter in the second, and a third meter in the third second. So after 3 seconds, the situation looks like this, right? So now, at t equals 3 seconds, s still measures x equals 2. The ball hasn't gone anywhere, right? But s prime measures x is equal to minus 1, right? And that's because they've moved relative to the ball, and the ball is now behind them. Okay? So not super duper complicated, but it does bring up an important point, which is if we want to know where something is, we need to check not only where it is, but we need to keep track of when we measured it, right? And so we talk about such a thing as an event, and there's not only a time when it happened, but also a where it happened, which could be 3 coordinates x, y, z that tell you, sort of this direction, and that direction, right? The other thing that we've shown is that importantly, time and space are not completely independent of each other, right? They're related by relative motion between observers, right? So different observers don't necessarily agree on what the spatial and temporal coordinates, well, what the spatial coordinates of an event are. Okay? As we'll see, it gets even more complicated. Okay. So, actually, I'll skip this one. One thing we can do is we can try to come up with an equation to convert measurements of position from one frame to the other, right? You can sort of imagine what it is, right? So basically what I need to do is I need to take the position in the stationary frame, x, and then to get the position in the moving frame, I just need to add how much the frame has moved. And that's going to be how fast it's going times for how long it goes, right? Because if I'm moving at 1 meter per second and I move for 3 seconds, I'll have moved 3 meters, right? And so this equation sort of captures that. It tells me that if I want to know what the position in the prime frame is, I just need to take the position in the unprimed frame and then subtract the velocity of the moving frame times t. So we can check that it works here. So for example, in our case, x was 2, v was 1, and t was 3, right? So 2 minus 3 times 1 is negative 1, and that's what we got back here, right? Okay, so this equation works. If it's a little mind-bending and too much math, don't stress it. But you can see that we can't come up with transformations that allow us to predict what the observer in the other frame would see, right? Or measure. And it gets more general, because we could move in x, y, and z. But the important thing is that baked into Newton's laws, there's sort of 2 things. One is that the laws of mechanics are the same in any inertial reference frame, right? And we saw that from the air hockey example, right? The puck doesn't just start moving and behave differently because we're in a cart moving at constant speed. If we went to a non-inertial frame, then things get hairier, right? But for inertial frames, the laws of mechanics are the same. We also have baked in the idea of inertial observers being able to compare measurements of time and space by using equations that look sort of like this one, but more generalized for motion in 3D, right? And so we get the distance between 2 points measured by the primed observer is equal to the distance measured between 2 points for the unprimed observer minus something that tells us how fast the observers are moving relative to each other times delta t, and it looks like that. And then we have the fourth one, which is time. In Newtonian physics, the 2 observers agree on time. Okay? So if you think that 3 seconds passed, I measure 3 seconds in the moving frame, you measure 3 seconds in the non-moving frame, and we agree on what the time interval between events is. If we divide everything by delta t here, we get that delta x over delta t, right? That tells me how much my position changes per time. That's going to be what my speed, right? And so we can also derive equations for how velocities compare between different frames. Okay, so one last thing about the sort of the Newtonian picture of the universe. In the Newtonian picture of the universe, and remember Newton studied light, we think that light moves in a straight line, right? I take a laser pointer I didn't bring the super bright one that I brought last time because I think it burned people's eyes. But if you point a laser pointer and it looks like the light shines out in a straight beam, right? Maybe we had some smoke. We'll up the effects budget for next time. But light appears to be moving in a straight line, which it turns out is also sort of the path at a constant speed is also going to be the path that takes the least time between 2 points. And so there's a theorem called Fermat's principle that tells us that light will follow the shortest distance / least time path between 2 points, right? And according to Newton, that's a straight line. Okay. All right. So fast forward, Newton's like mid-1600s. Fast forward to the mid-1800s. There's been a bunch of experiments done on, how are we doing on time? Okay, on how electricity and magnetism works by a bunch of people. Faraday, really interesting guy if you want to read about. He came basically from nothing, got a job as an assistant bookbinder, and then went on to become one of the greatest scientists of all time. Anyway, Faraday, Coulomb, Biot-Savart, Ampere, and others do a bunch of different experiments and show how electric and magnetic forces work. These are all summarized eventually by Maxwell into this system of 4 equations that tell us how electric and magnetic fields work. Don't worry if you don't follow these. And Maxwell is able to show that if we assume that there's no charges anywhere and there's no electrical currents anywhere, they reduce to this. And these can be simplified to an equation that looks like this. Now, for physicists, this is a really exciting thing because this is called the wave equation, and we know how to solve it. It tells us that there should be electromagnetic waves. And then furthermore, it has this parameter of 1 over c squared. And this tells us, this c here is how fast the wave moves. And if you go and you plug in your numbers from Maxwell's theory, you get that it's about 3 × 10⁸ meters per second. Does that ring a bell to anybody? This is kind of a weird one. It's the speed of light, right? So this is interesting because it tells us these electromagnetic waves, that light could be an electromagnetic wave, right? And so one last thing before we go to a break. So Maxwell's theory predicts that there's these electromagnetic waves, probably light, that travel at the speed of light. But he doesn't say relative to what, right? And then furthermore, and if you change reference frames and use Maxwell's equations, you basically still get C, which is kind of weird. And then the other thing he doesn't say like what these waves propagate through, right? So we know that sound, for example, propagates through air. Water waves propagate through water. So there's something mysterious about these electromagnetic waves. So I'll stop there. We have a 10-minute break. And then we'll get back to it and get to what Einstein has to say about all this. And so then I can flip this around to get that the time that it takes is going to be how fast the rocket is going, dividing by how far it has to go. Okay? Oops, I flipped those around. Yeah, that should be L naught over V. Quick, look there. No, too slow. Whatever. Let's. I shouldn't have done that. Too many slides. Okay, we'll start there and just go for it. Okay, now the other option is we can measure. We can ride along with the astronaut and try to see how long it's going to take them, right? And maybe I'll skip the quiz portion of this. But how long does it take? How long does the trip take according to the astronaut? Well, according to the astronaut, the events of leaving the Earth and arriving at Saturn happen at the same location. So the time interval that they would measure is going to be the proper time. Well, that proper time can't be the same time that the people on Earth measured, right? Because we know that the astronauts are moving relative to the Earth. So this equation here tells us that delta t and delta tau can't be the same number because this v here is not 0, right? So this tells us that delta tau can't be the same time that the people on Earth measured, right? Okay, well, that means that something's got to give, right? Because something's got to give, right? Okay, so what has to give? Well, what are some things that the astronaut and mission control must both agree on? Well, we already know they don't agree on the duration of the trip. we would think that maybe they would agree on the distance between Earth and Saturn, right? But we know they definitely agree on the relative speed between them, right? If I see you driving 60 miles per hour that way, you see me going 60 miles per hour this way, right? So that third one they definitely agree on. The middle one is like, it seems like they would, but let's see what happens. Well, it turns out that the only thing that we're going to agree on is the third one, right? Because if we go and we try to measure, sorry, I'll skip these for sake of time. If we try to measure the distance, say between, let's say the Earth is here and Saturn is here, right? Then we measure that distance L naught. The time between events of this observer going from here to there is delta t, according to the observer S. Then the speed of the moving observer is just L naught divided by t, or by delta t, right? How far I go divided by how long it takes me, right? In the other frame, and what I ultimately want to check is whether the length of the distance between Saturn and Earth is the same. We'll call that length L prime because it's according to the primed observer. The time between events is delta t prime, right? So the speed of this guy, according to the primed observer, is going to be the distance that I measure in my frame S prime divided by the time that it takes me to do it, right? How are those related? Well, we know that this delta t prime and this delta t are related by the time dilation formula, right? This gamma here is that 1 over square root of 1 minus v squared over c squared. Okay, but so if I agree on v, I disagree on delta t and delta t prime, right? Then can I possibly agree on L naught and L prime? No, you can't, right? Because I'm taking some number, dividing it by number a, right? And then I'm taking potentially the same number, dividing it by a different number. I'm not going to get the same thing, right? So basically, these two observers can't agree on the length and the distance between Earth and Saturn, right? And so that's a secondary effect called length contraction. And it'll turn out that the length in the moving frame is actually shorter than what's called the proper length, which is the length in the stationary frame. Right? So those are two weird effects that Einstein derives very sort of quickly, and he arrives at sort of a new conclusion that we really can't compare positions and times the way that Newton and Galileo tell us, but instead we have to use these more complicated formulas. I won't get into the details of how you derive them, but it says that if we want to know the position in the prime frame, we need the position in the unprimed frame, the time in the unprimed frame, and then also this parameter gamma, which is related to how fast we're moving relative to each other. But then also time gets mixed in with space too. In order to know the time in one frame, I need to know the time in the other frame, but I also need to know the position in the other frame, right? And so we can no longer really talk about sort of like space being one thing and time being a separate thing, because now they become intertwined and we get what is now known as space-time. And we always have to keep track of all four things, X, Y, Z, and T, and they're all interrelated between observers that are moving relative to each other. Okay, so this is really kind of mind-blowing. And it's a whole week in my modern physics section class, but I'll stop there, right? Now, what about non-inertial observers, right? So way back in our Einstein slide here, right, we said the laws of physics are the same in any inertial reference frame. So what about non-inertial frames? Well, it takes Einstein about a decade to figure out what happens when you let the observers accelerate relative to each other, right? And how that works is way outside of the scope of this talk, but I'll give you a little taster here. So I'm going to talk about something called the principle of equivalence, which Einstein described as the happiest thought of my life. And so he's sitting around for a decade trying to figure this out, and finally this dawns on him. And from there, he's able to then make all the math work, right? So the idea is the following. Suppose we have Einstein, and he's sitting on the Earth's surface in a box. He can't really see outside of it, so he can't tell whether he's moving or not relative to the Earth. And he's standing, he feels weight, right? He pushes down on the floor pushes back up on him, he kind of feels that he has weight to him. If we have, I don't know, his lunchbox or something, when he lets it go, it falls and it accelerates as Newton told us, right? Or as the Brian Cox video showed us, it just falls down, right? Now, what Einstein realizes is that I can't really differentiate that from being in a rocket that's accelerating the other way, right? So if I was just out in space, I'd be floating around, no gravity, right? The lunchbox would be floating around, no gravity. But as soon as that rocket accelerates, the rocket pushes on my feet, right? I feel like I'm being pushed up, kind of like I was standing on the Earth. And the lunchbox, which is just floating in space, according to me now, accelerates downwards, right? Because it just gets left behind by the space elevator thing, right? Conversely, if I'm in space and there's no anything massive nearby that's going to exert a significant amount of gravity, right? Einstein's just going to be floating around. And nothing falls. Everything just kind of floats around, right? The lunchbox floats, right? This turns out to be equivalent to just free falling towards Earth. So that's sort of like the equivalent of the video with the feather and the bowling ball, right? If rather than the bowling ball we had Einstein, right? Einstein would fall with a feather, and to him, if he wasn't looking at the walls of the vacuum chamber, it would just look like he's floating with a feather floating in front of his face, right? Okay. So this idea is called the principle of equivalence, and Einstein basically concludes that no experiment can distinguish between being weightless in sort of remote space or being in free fall near a massive body, right, falling under gravity. And conversely, that if you're in an accelerating frame, you can't really differentiate that from being in a gravitational field, right? Okay, now let's think about what that does for light. So, and by the way, this is sort of also importantly tells us that there's no experiment that can distinguish between the two. So I can't do any experiment that tells me that I'm floating in space or free falling near a gravitational object, or in a gravitational field, right? Okay, so let's do an experiment. So suppose that we have a space shuttle just floating out in space, far away from anything that exerts a gravitational field. We do an experiment where we shoot light out at A, it hits a mirror at B, right, or a detector at B, and we measure the time or something, right? That's one experiment that we could do, right? And this is free floating in space. But we said that we should get the same result if we do the experiment in free fall instead, right? We're near a gravitational, we're in a gravitational field, and we do the experiment in free fall. So in that case, what's going to happen? Well, suppose that the Earth is down below, right, and the space shuttle is going this way. What's gravity going to do? It's going to cause it to like curve down, right? It's kind of like throwing a ball, right? And so the space shuttle is going to do this, right? But that light in that reference rate, in that situation, must follow a curved path and hit the front of the space shuttle here, right? Because otherwise I could tell the difference, right? Otherwise, in the free-floating situation, the light would hit the front of the shuttle, and in the falling situation, the light wouldn't hit the front of the shuttle, right? So what this tells us is that if we have a gravitational field, then light is going to follow curved paths, right? So now putting all this all together and skipping a ton of steps in between, this tells us that if we have a massive object, because it exerts a significant gravitational field, it's going to warp how space-time works, and it's going to make it so that straight line paths, or the shortest sort of time paths in a particular definition of shortest path, are no longer straight lines, and so light is going to curve, right? So you shoot your laser, and rather than going like this, it goes like that, bends in this curved space-time. Now, this is, of course, super mind-blowing and weird, and that's why it took a long time for people to figure it out and for it to be accepted. So let's think about what happens. So now finally we're getting to the eclipse stuff. Suppose that we have a star, and it is over here. And let me put the little laser pointer on. So we have a star here, right? And we can tell where it is, if we now ignore the sun here, by just looking at what direction its light is coming from. If there's no gravitational field, significant gravitational field between it and the Earth, light will travel in a straight line, and we will determine that the star is sort of in that direction, right? Now, on the other hand, if we have something massive that generates a significant gravitational field, that's going to distort space-time, cause light to go in a curved path. It'll turn out that it will cause it to curve towards this massive object, which in our case is going to be the sun. So there's some light that goes this way, and it just gets absorbed by the sun, and we don't even see it. But there was some starlight that was originally going this way and would have missed the Earth, and we wouldn't have seen it. But instead, it'll curve around the sun and appear to be coming from this direction. Right? So basically, the position of the star will appear to change when the light goes near the sun. And Einstein goes ahead and is able to predict this angle here by which the direction of the light changes. And it's this big combination that depends on how massive the sun is, right? More gravitation, more bending of space-time, more deflection. How close we are to the sun. Remember, gravity falls off the further away we are from the sun, so the effect should be smaller when the light is passing, like, say, out here. And then there's a speed of light in there squared. But at the end of the day, we can combine all these constants into this number L here, and then it just tells us that the deflection is going to depend on how far we are from the light passes from the center of the sun. Okay? So now if we look, so this is looking at it sideways. Now, if the main problem here, though, is, well, what happens if I try to image stars that are sort of near the sun in the sky, like today? Can I take pictures to try to measure their displacement? Well, okay, yes, not Oregon. If we were in Arizona and we're trying to take pictures of stars that are near the sun in the sky, can we do that? No, your camera just gets completely blasted by the sun and we can't see it, right? So in order to test this, we actually have to wait for a total solar eclipse when the moon is going to cover up the sun, and then we're going to be able to see the stars in the background, right? Because the light needs to pass near the sun in order for us to measure this effect. Okay, so what's going to happen? So now if we're in a total solar eclipse and we're looking up at the sun, right, after its totality, and we can do it safely, right, then what's going to happen? Well, the stars that are sort of a little bit sort of towards the top of the sun, the light is going to curve this way, and they're going to appear to move up. The ones that are like a little bit below the sun, their light is going to curve up like this, and they're going to move down, right? Same thing left and right. And so what's going to happen is if we're looking at the sun, the little stars will appear to move radially outward away from the sun. Okay? Now, how much do they do that? Well, we can take all those numbers, the mass of the sun, the radius of the sun, all the stuff that Einstein got in his formula, plug in the numbers, and what do we get? We get something called we get that L should be 1.75 arc seconds, and we'll define that in a second, divided by how far the beam of light passes from the center of the sun in units of solar radii, but that's not super important, right? Okay, so how small is an arc second? Well, an arc second turns out to be 1/60th of an arc minute, and 1 arc minute is 1/60th of a degree. So 1 arc second is 1/3600th of a degree, right? Now, how small is 1 arc second? Any guesses? Like if I was measuring the angle like this, like how big is 1/3600th of a degree? It's super tiny. So for comparison, 1 arc second is about the distance in angle between the top and the bottom of a dime as viewed from 2.5 miles away. So we're talking really, really tiny angles, right? So the star was there, and then its position moved by 1.25 arc seconds, and we're trying to measure that. It's not like the star is there and it moves to there, and then it's like, I can do that by eye, that's fine. No, this is very, 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 very small displacements, and they get smaller, right? Because this says that it's 1.75 arc seconds divided by r. So as r gets bigger, this effect becomes sub-arc second changes in the positions of the stars. So you can see that this starts getting pretty hairy. But in fact, people pretty soon after, Einstein actually kind of gets a little bit lucky because in 1911, when he first published his result, it's off by a factor of 2. And people try to measure it, but are unsuccessful for a variety of reasons, including World War I kicking off. And then during that time, he finds his mistake and gets the factor of 2 and makes a prediction. And then in 1919, two astronomers, Eddington and Dyson, set this big expedition to go and try to measure this effect. And they go to Sobral in northern Brazil here, and to the island of Príncipe off the coast of, I think it's the Ivory Coast, I can't remember, or Equatorial Guinea or somewhere. Anyway, off the coast of Africa. And they have these big, massive telescopes because the photographic technology is very primitive, right? The plates are not very sensitive. They need big, massive telescopes to gather a lot of light so they can take images. They don't know the positions of the stars super well, so they not only need to do the experiment during the eclipse to measure the positions of the stars, but they have to wait 6 months, leaving these telescopes. Hopefully, nothing changes at all until the Earth is on the other side of its orbit, so that the stars that were behind the sun are now, the sun is behind you. And they go and they end up getting 2 pictures. But analyzing them, they're able to measure the positions of 7 stars, and they do find a displacement radially. This is just cartoon version here. And they can plot sort of what you would predict if Newton's sort of theory of space-time was right and what Einstein's theory of space-time was right. And their results, if you squint, kind of suggest that Einstein is right. Well, what happens? They go and they report this at the Royal Society, and within days, Einstein sort of becomes a household name. So the Times of London says, revolution in science, new theory of the universe, Newtonian ideas overthrown. Right, for Brits, this is a big deal because Einstein was Newton was kind of their guy, right? And had been dominating physics for 500 years, or 400 years, right? So overthrowing Newton is a big deal for the Brits, right? The New York Times a couple of days later says, light all askew in the heavens, men of science more or less agog over the results of the eclipse observations. Einstein theory triumphs, stars were not where they seemed or were calculated to be, but nobody need worry. And then they also discuss his book on general relativity, which he says there's maybe only 12 people on the planet that can understand it. And no more in all the world could comprehend it, said Einstein when his daring publishers accepted the book. Anyway, at this point, these long-standing ideas in physics are sort of shown to be wrong. And Einstein really kind of takes off as a household name and becomes a rock star. Okay, now, obviously, as I showed here, Eddington's experiments were okay, but not super duper necessarily accurate or convincing. So over the years, many people tried to replicate these experiments. So here's a graph that shows sort of time, starting in 1919, and various predictions. This parameter here, if this is 1, then Einstein is right. And you can see that these early experiments have huge error bars. Some of them aren't even in this graph. They've got measurements way up here. And all of these red ones are done using optical telescopes, so basically recreating what Eddington does. Here's a plot of that displacement of the stars as a function of distance from the sun. You can sort of see that it fits that 1 over r curve that Einstein predicts. Right? In the 60s, we get radio telescopes, and radio telescopes kind of free things up a lot because it turns out the sun doesn't emit a lot in the radio. So we can actually look at the stars, at radio sources from space, even while the sun's in our field of view. So they're able to take a lot more measurements. Eventually, they get really sensitive radio telescopes, and they're really able to pin this down to sort of a ridiculous level of accuracy. So here are these sort of latest radio telescope measurements show that Einstein is right to 1 part in 10,000. So very. On the other hand, the optical experiments kind of stopped once the radio becomes popular. There's some that are done with space-based telescopes. So Hipparchus is a space-based telescope. And there's another sort of interesting set where they, rather than using light curving around the sun, they use light curving around entire galaxies. and that's called galactic lensing. But anyway, by the early 2000s, Einstein's theory of relativity is pretty much assumed to be correct to a very high level of precision. Okay, now there are some challenges if you're actually trying to replicate Eddington's experiment. So first off, you need your exposures of your images are kind of tricky because during an eclipse, and I imagine most people were here for the 2017 eclipse and hopefully saw it, even though the sun is blocked, you still get the corona, which is relatively bright. So you're trying to shoot against a relatively bright background, and you really want the stars that are close up near the sun. So you kind of have this balance of if you expose too long to get those faint stars, then your image is washed out. If you don't expose long enough, then you don't get the fake stars. So there's kind of this tricky exposure situation. Also, the atmosphere is always constantly bubbling and churning with different temperature air. And that turns out acts like little tiny time-dependent lenses that are distorting the path of light. And so you'll actually see that if you look at a star in a telescope carefully, it will jump around, right? And this, in fact, is why stars twinkle. So if you were out in space, stars would just be a constant brightness. But because the light is coming at us and sort of sometimes it might be coming straight to your eye, but then a second later a blob of gas passes by and distorts the direction and now it hits your forehead. So the light beam is doing sort of this around your eye. That's why we see twinkling stars, not because the stars are actually changing brightness, right? Turns out the stars, even though they don't appear to change their positions relative to each other very much, do in fact, because they are these giant balls of plasma that are like zipping around the universe, just like everything else in space. So you need to know their positions very well, and you need really up-to-date and precise star catalogs. There's other weird effects, like, for example, the starlight, when it's coming through space in a straight line, then it hits the atmosphere and it bends, kind of like a ray of light bending when it enters water, right? And so that changes the apparent direction of the star a little bit. And then there's a relativistic effect, which has to do with the fact that the Earth is moving relative to the stars. And so remember that Einstein tells us that the speed of light, imagine that's the size of this little vector, has to be the same no matter what reference frame we're in. So if that's c, and then we're moving, well, you would imagine that there would be a bigger component of this vector in the horizontal direction. That means that there has to be a smaller component in this direction to make up for it. That's sort of a technicality. Don't stress it if it didn't make a ton of sense. But basically what I'm trying to capture here is that there's sort of a lot of effects that are conspiring against you when you're trying to replicate Eddington's experiments. And that's before we even get into errors introduced by the telescope, right? So a telescope, the lenses might not be perfect, and so you might get optical distortion introduced there. So let's look at the sources of error. We have optical distortion just from the telescope's manufacture, right? That can be on the order of 3 arc seconds. Now remember, we were trying to measure like 0.1 arc seconds, right? You have atmospheric refraction, and that's going to be on the order of 2 arc seconds. And then we have the wobbling from the atmosphere. That's about half an arc second, so that's another problem. And then we have these 2 additional sources of error that can be smaller, right? So we were trying to do measurements where the errors are sort of bigger than the measurement, which makes it really, really hard, and we have to do very careful calibrations. Okay, we have 50 minutes. Okay, so enter, in 2017, an amateur astronomer called Don Bruns attempted to do the Eddington experiment, and he is able to do it and do basically the most precise version of the Eddington experiment, so using ground-based optical telescopes by exploiting modern technology. So let's talk about how he did it. So the first thing is he's able to use digital cameras, right? Digital cameras allow us to take a ton more images than Eddington, right? Eddington had to wait for those plates to expose. If throughout the whole eclipse, he's only able to do 2, right? Don is able to take, tens of images. And he's able to do it with a much smaller telescope because he doesn't need that really big light gathering ability that Eddington required because of the low sensitivity of his plates, right? And so I'd be able to pull out like little stars near the corona here. You can also take a ton of images and kind of average the noise out. So for example, if we just looked at one of Don's pictures, it might look like this, and you're like, I don't know if that's a star or not. But if you take a bunch of them, the noise around it is going to be random, And so you add a bunch of them together, it's going to cancel on average, whereas the signal from the star is going to build up. So you can actually pick out fainter stars by taking a bunch of images and averaging. Turns out we can also cheat. So Eddington had to wait 6 months and take reference images and whatever. We have the Gaia satellite, which is from the European Space Agency, and it can measure the positions of the stars to, what's that, like, well, 0.00000024 arc seconds, right? So for our purposes, we basically know the positions of the stars perfectly, right? Because we're only really looking for deviations on the order of 0.1 arc seconds. So that gives us references that are sort of the ground truth. Okay, that's a big cheat. Okay, we're also able to correct for optical distortion, so we can look at a star field not near the sun and a star field far away, and basically compare the positions where we measured the stars in the reference star field to those from the Gaia catalog. And then that tells us basically how distorted and not perfect our telescope is. And I won't get into the details of how we do that correction. If you want to learn about it, you know, it gets a little technical, but I can explain it after. And we can correct for those. So we can basically subtract out those distortions. And then Don was able to replicate the experiment and actually get what is sort of the best Eddington experiment ever. You know, and sort of comparable to what NASA is doing with galactic lensing, right? But this is just one guy with like $5,000 worth of equipment as opposed to NASA with $1 billion satellite. Okay, so fast forward to 2024. So me and a couple of those students, and then Don and a team from Portland Community College decided to try to even improve on Don's experiment, basically by using newer cameras, increasing the number of telescopes so we can take more and more images, get better and better statistical power for our measurements. And then also Don did a ton of processing the images by hand. We worked to write some software to make the analysis a lot simpler. And then ideally, if everything had worked, we could have probably challenged, you know, these really precise radio telescope measurements. Now, for the eclipse, we wanted to make sure we were somewhere where there wasn't going to be clouds. So here's a cloud cover map, and you can see that Mexico here has a low chance of clouds, whereas up here in New England, there's sort of a large chance of clouds. So we decided to make sure that we got here, right? And we set up sites here in El Salto, Durango, Mexico, and in Ciudad Canatlan in Durango, the state of Durango, and then in Leakey, Texas, outside of San Antonio. Now, there's one problem with going to Durango, Mexico, and that's that it's kind of in the middle of nowhere and is not really known for anything other than being the birthplace of Pancho Villa, a place where a bunch of Westerns were shot back in the 50s and 60s, and the home of just giant scorpions everywhere. The other problem that it has, it is beautiful though. It's up in the mountains, really kind of remote. We had a journalist from the Washington Post come with us, and he was a photographer, news photographer in Mexico. He said this was the first time in 20 years of doing news photography that he'd been to the state of Durango, and it was the only state that he'd never been to before. So this is kind of out in the middle of nowhere. Well, out in the middle of nowhere in Mexico kind of creates some problems, because it turns out that Durango is part of the golden triangle of the Mexican drug trade. So most deans would have said, you absolutely cannot take students there. I, on the other hand, had been talking with locals, very carefully talking to the police, the federales, and everybody, and was able to sell my dean into letting me do this. And it actually turned out to be awesome, because basically, because of the eclipse, they really wanted no problems, and so the security forces were out like en force. My students were kind of a little bit agog when there was like trucks of guys with machine guns walking around. But anyway, so we went there. We also needed to get the telescopes there, so Toby Dietrich from Portland Community College actually drove them from Portland in a trailer. It was his 1973 Volvo. It was kind of an ordeal. He drove to Nogales, and when he got to the border, they were like, "What's in the back?" He's like, "Telescopes." "Oh, those, how many do you have?" He was like, 5. like, oh, you can only carry one telescope per person, and otherwise you have to pay import tax. How, and he's like, okay, how much is it going to be? Oh, that's going to be like $5,000. I was like, uh-oh, we can't pay that. So then Toby had to leave the telescopes in Nogales, drive back to Portland, because he had to teach. Then we spent like the next 6 months basically trying to learn about import-export law. We finally figured out how to get them into Mexico using something called an ATA carnet. If you want to learn about the subtleties of import-export, I can talk about those after. Eventually, like 5 days before the eclipse, Toby and his student Hassan drive down to Nogales again, pick up the telescopes, and hoof it down the Mexican coast. They get to Mazatlan, start going up the mountains, and the old faithful Volvo breaks down. And so we were like 2 days before the eclipse. The telescopes are in the middle of nowhere. Luckily, the guy that was going to host this, who is right here, his name is Jeff. I actually don't know his last name because he wouldn't tell us what his last name was. But he had a compound. He had a compound in rural Mexico that was like near the vice president of Mexico's like summer house or something. Anyway, it was also a bar for bikers. So here are me and my students basically planning everything at the bar. But Jeff hosted us and went and picked up Toby and the telescopes. And by the time we got there, the telescopes were rolling in, and everything went sort of okay. And so then we spent the next week or so aligning telescopes, working with the students to do everything that we didn't have time to do over the winter here in Oregon when we really couldn't image anything. And so they did a great job. And then we did a lot of outreach. We went out into community, gave out about 2,000 pairs of eclipse glasses, gave instructions about like how to safely watch the eclipse, dispelled a lot of myths. So there was a lot of things about like if a pregnant woman sees an eclipse, then she'll miscarry and kind of stuff like that. So we gave a lot of public outreach. We didn't have a printer, so I had to like hand make a QR code for the instructions. That was kind of fun. And then on eclipse day, after 4 days of no clouds. So luckily, I mean, there were high clouds and relatively sparse, and so we actually were able to gather some data and make some measurements. They're not as good as we wanted them to, and we're still in the process of sort of trying to suss out as much information as we can. But we do see that if you look at the little cross here, it's a little bit shifted from that blue dot, and that's the displacement of the star relative to the position that we expect it to be. And so we have some preliminary results. They're pretty noisy, but they do give us that L is about 1.84 with error bars of 0.24. So our error is sort of comparable to some of those earlier experiments. Doesn't quite get what we wanted and doesn't beat Don, but we're working on making those better. Okay, I'll skip that part. And then the last thing is we're trying to do it again. So if anybody has some money they want to spend and fund me to fly to North Africa in 2027, it's going to be the best eclipse for this type of experiment in like the next 140 years. So we're currently making plans for 2026. There's going to be an eclipse that goes through Spain and Portugal, doing some test runs there, then doing 2027, and then maybe 2028 in Australia. With that, I will thank my team and Jeff, whose last name we don't know, and also the Office of the Dean and the Engineering Excellence Fund for funding this whole ordeal. And I'll stop there and take any questions.
I think we may have time for one question, and Mark put his hand up first.
I was just going to make a quick suggestion for your next visit in Europe. Avoid Benghazi, Libya.
Oh, well, actually, so do you happen to know exactly where Benghazi is? It's like right here, which is like the sweet spot. But I think that one might not fly with the dean. So right now we're thinking about Oza, Egypt here, or Tunisia. So I'm actually working with an anthropologist at Reed College who specializes in Northern Africa and is trying to help me out, figure out where are the places that are reasonable to go. Apparently, the Algeria's mess. Morocco is too close to the ocean, so the imaging conditions aren't great. All right.
Okay, I'd like to thank Dr. Barrero very much for this presentation, and I thought it was great. We could follow it. He did a fantastic job at a complex subject to us, so thank you very much.